All right, one of our major topics in this section is going to be on polygons. So let's discuss some of the polygons that will be really familiar to us, triangles and quadrilaterals. So a triangle that contains one right angle, you call that a right triangle. And if the angle, so triangles are generally classified by their angles. If you have all acute angles, call that an acute triangle. If you have only one obtuse angle, call it an obtuse triangle. All right. So interesting. I wonder if a triangle can have more than one obtuse angle. Should think about that. And I think there's a homework problem about that. If you have a triangle where none of the sides are congruent, call that a scalene triangle. But if at least two of the sides are congruent, we'll call that isosceles. It's an isosceles triangle. And a special type of isosceles triangle where all the sides are congruent is called equilateral. An equilateral triangle. Okay, so one thing to notice. Every equilateral triangle is an isosceles triangle. Some isosceles triangles are also equilateral. All right, what is this object here? A quadrilateral, so quad meaning four-sided object, polygon, that has at least one pair of parallel sides is called a trapezoid. All right, now if you have a quadrilateral where two adjacent sides are congruent and the other two adjacent sides are congruent, that's called a kite. Notice here's an example of a convex kite and here's a concave kite. Now, this is a trapezoid again. If it turns out that your trapezoid, again, which has a pair of parallel sides, also has base angles that are congruent, then you call that an isosceles trapezoid. Okay, if you just have that the base angles are congruent, that actually turns out that these two sides will also be congruent, and then these two angles you get will be congruent for free as well. We'll see that in the next section, why that is true. This object here is called a parallelogram. It's a quadrilateral with two pairs of parallel sides. So notice that every parallelogram is also a trapezoid because each parallelogram has at least one pair of parallel sides. Some special trapezoids are parallelograms. If you have a parallelogram and you force one of these angles to be a 90-degree angle, to be a right angle, what you get is a rectangle. Because all these sides are parallel, when you force this angle to be a right angle, that'll push all the angles to become right angles as well. All right, some parallelograms are rectangles. Every rectangle is a parallelogram, right? Because here's a pair of parallel sides, here's another pair of parallel sides. If you take a parallelogram and you force two adjacent sides to be congruent, sort of like a kite, what you get is a rhombus. Right? Because some parallelograms are rhombuses. Every rhombus is a parallelogram. Also, this whole business about adjacent sides being congruent, that was what we saw in the definition of a kite. So every rhombus is also a kite. Some kites are rhombuses. Every rhombus is a kite. Okay, now we'll see that play out in this hierarchy of quadrilaterals, right, and triangles as well. In the world of quadrilaterals, okay, we've got trapezoids, we've got kites. These are not necessarily the same. There's no hierarchy between these. They're not subsets of each other. Kites are a subset of quadrilaterals. Trapezoids are a subset of quadrilaterals. Some special properties that you force on your trapezoid, you can make base angles congruent and get this subset where you get isosceles triangles. You can force the other pair of opposite sides to be parallel and you get this subset of trapezoid, which are called parallelograms. If you have a quadrilateral that is both a parallelogram and a kite, where you have opposite sides are parallel, and also that the that adjacent sides are congruent, what you get is a rhombus. Wonder what goes here. What type of quadrilateral is both a parallelogram and also an isosceles trapezoid? So it's like a parallelogram where the base angles are congruent. That would have to be a rectangle. And what special quadrilateral is both a rectangle and a rhombus? That would be a square. So this is your hierarchy amongst quadrilaterals. All right, so the thing to note here, every square is a rectangle. Only special rectangles are squares. All right. Now let's move on to symmetries. All right. We'll have a couple different types of symmetries, line symmetries, turn symmetries, and point symmetries. You've likely had some of these activities when you're a kid. You hold the mirror or the mirror up against the line of symmetry so you can draw the other side of your object. So what we say is figure has a line of symmetry if it is its own image under a reflection in L. So here's my line L. What you do is you take this object and you reflect it, keeping that line in place. And if you get the same object after that reflection, then you have a line of symmetry. Let's look at these examples. I'd like you to pause the video, draw in your lines of symmetry. How many lines of symmetry do we have here? Well, we have one line of symmetry in between each pair of opposite vertices. So that's 3 lines of symmetry. We also have a line of symmetry in between each pair of opposite sides. We do that very well. So there are 6 lines of symmetry for the hexagon, which would make sense. The letter A is exactly 1 line of symmetry. This almost oval shape here has a line of symmetry vertically and also a line of symmetry horizontally. So we've got 2 lines of symmetry. The letter Z, 0 lines of symmetry. It has some other type of symmetries, but no lines of symmetry. Now let's discuss rotational symmetry. You say a figure has rotational symmetry if you can rotate the image about some point, which is called the turn center, so that it matches the original figure. So here's an example, this leaf-shaped object and this triangle. You take the turn center, keep that in place, and rotate this vertex over to that vertex, and you'll see that you get the same shape again. So now we might be interested in figuring out, you see I've got a 120-degree rotation here to achieve the same object, the original figure. We might be interested in knowing what is the angle of turn symmetry. So let's do a few examples there. Starting with this example that we see, how do I know I have a 120-degree rotational symmetry here? What I'll say is that 360 degrees is all the way around. I can rotate A to B, or A then from B to C, and then from C back to A to achieve that 360 degrees. So that was 3 turns it took me to get all the way around. So if I take 360 degrees, divide it by the 3 locations, symmetric locations, the 3 turns that it takes, gives me my 120-degree turn symmetry. All right, let's see that played out in these examples. Actually, I'd like you to pause the video and try these on your own. Find the amount of turn symmetry for each of these figures. All right, for this first one, my turn center is right in the middle, and I can actually draw out the angles of turn symmetry here. So I can turn to put this vertex here onto this point. So that's my first turn, second turn, third turn, fourth turn, fifth turn. Notice that the number of turns is the same as the number of vertices. So here I've got 360 degrees divided by 5, which should give me 72 degree turn symmetry. So this angle right here is 72 degrees. All right, similarly here I've got 1, 2, 3, 4, 5, 6. I've got 6 vertices, which will allow me to have 1, 2, 3, 4, 5, 6 turns to get back to my original figure. So 360 degrees divided by my 6 turns gives me 60 degree turn symmetry. This one is interesting. You put your turn center in the middle there. The only angle measure that would make sense for me to turn my object and match the original figure is if I move this vertex here to this vertex right here. And that can be done with a 180 degree turn symmetry. So I'll turn it from here to there and then back again. That's exactly 2 turns to come back to my starting place. So 360 degrees divided by 2 gives me 180 degree turn symmetry. And actually, if you have 180 degree turn symmetry, that's a special type of turn symmetry called point symmetry. So each one of these objects here has point symmetry, because if you turn the object 180 degrees, you'll arrive at the original shape.